Hello everyone, my name is Andrew and today I'll be doing a presentation on my instrument design project. The ultimate goal of this project was to have a better understanding of the different factors that makes up of a wave. For example, the wavelength, the speed of it, the amplitude, the frequency, and so much more. An overview of today's presentation will look like the following. Firstly, I'll be talking over the materials that are required to make my instrument. Secondly, the characters and the unique adaptations of my instrument. Thirdly, how sound is produced in it. Fourthly, the adjustments of amplitude and frequency of it and how they affect the instrument and what they look like in everyday life, as well as a little bit of further elaboration on them. Sixth is the character of the quality of the sound produced, which means what kind of sound, what does it sound like, and similar to that. Seventh is some calculations of it, and last but not least, I'll be doing a demonstration with these bottles here, all filled with water, but with different volume in it, and see how those changes the characters of the sound. Now moving on to the first actual slide, which is the materials that are required to make this instrument. As you can see from right here, we have 3 bottles here filled with different amount of liquids. Right off the bat, we know that we need some type of bottle, and beer bottles are the best because they are closed at one end and the amount and their top is just perfect enough for the perfect amount of air to flow in and out of it. However, plastic bottles will also work. One essential key factor to it though, it must be a closed air column. What that means is that it is open from one end, as you can see, has an opening here, however closed from the other end, and this is very crucial to the experiment. Secondly is that you need some type of liquid in these bottles, and I chose water. Thirdly is that you can have a cardboard box for you to hold all of these instruments if you like. However, I decided not to do that just because there's not really a point to. Now, characters and adaptations of my instrument. Firstly, we have to realize that beer bottle is a closed air column. Now that's out of the way. There's a few things that we need to clarify about sounds. Sound is a type of energy that is created by vibration. If it's vibration in air or any medium, in this case it would be in the water. Blowing air into a bottle creates difference in the pressure, and bottle pressures force more air out than more air that is coming in. And we know that with different pressure and the different flow of air, it creates a pressure of increase and a pressure of decrease, which ultimately causes a wave inside of these bottles with the air molecules, and that is how the sound is produced. Lastly, my instrument categorizes as a wind instrument, just like saxophone or the flute. Now, how exactly is sound produced in my instrument? I'll be talking about that right now. Firstly, blowing air into the bottle from the side is very essential as it allows air to flow in, however also allowing some of the air to flow out as well. And secondly is that air molecules will vibrate with your blow into the bottle, which creates sound waves as the air molecules vibrates inside of these spaces. Lastly is that with the decrease and increase in air pressure, it causes the air molecules to travel as a wave-like motion, which ultimately it turns out as sound in the end. Now, the adjustments of amplitudes. As you can see, there are 2 graphs here. The one on the left shows the low energy graph, and the one on the right shows the high energy graph. We can see and we know the fact that amplitude is measured by the distance from the midline to its maximum or its minimum point. We can see that the distance here is much less than the distance we see from here, and that's how the difference is made. Right off the bat, then we know that how much energy is put into the bottle, which indicates how much the amplitude is going to change by. More energy means you blow harder into the bottle, less energy means you blow softly. And however, secondly, not as significant, however it will be important in our everyday setting, is the surrounding environment and the medium that it is in. For example, you apply the same amount of force into the water to create a wave would be very different than if you were to blow into a bottle. For example, in order for you to make a small wave in water will probably be enough energy for you to make a fairly loud sound with these, as the density of water is greatly significant than the density of air. Now, like I said earlier, here you have a graph of what it will look like if you blow softly, and here of what it will look like if you blow hard into these bottles. Now the adjustment of frequency. Right off the bat, we have to characterize and define what frequency is. In instrument and in music, we state that higher the pitch causes higher frequency, and that's how the instruments and musicians define it. However, as a physicist and in reality, we know that frequency is characterized as the vibration per second with the SI unit of hertz. Now, we see that here are another two graphs of higher frequency at the top and lower frequency at the bottom. Now, I will be explaining what you can do in order to change the frequency. Firstly, if you have more water, it gives the air molecules less space to vibrate, which means it has to vibrate faster, which causes a higher pitch. And like I said here, a higher pitch leads to a higher frequency. Now, vice versa. If you have less water, it gives the air molecules more space to vibrate, like we can see over here, and it will vibrate slower as a result, which means to a lower pitch. And as you can see from the definition, lower pitch leads to lower frequency. Now, characterize of the quality of the sound that is produced from the instrument. Now, what this question means is what kind of sound and what does these sound like while they are produced. My instrument makes an airy sound, just like many other wind instruments, such as the flute, the organ pipe, and many more. It sounds like the back of your head, but you can't really describe it in words. However, when I do my demonstration of my instrument, or if you search up sound of flute online, it is, you know what it sounds like. Now, it is very common among many wind instruments to produce a similar sound. However, with different adjustment to the frequency and wavelength, they all sound very differently. Now, here's some calculations that I have done to find the wavelength and the fundamental frequency and what it looks like in everyday scenario. Now, the first calculation states the question that somewhat similar to the organ pipe, the homemade instrument beer bottle also resonate at best at its fundamental frequency, close to one end. The length is around 15 centimeters long. The speed of the sound in air is 342 meters per second, which is a constant given. Now, it asks us to find the wavelength and the fundamental frequency. Here I draw a diagram. We know that given in the question, 15 centimeters long gives you 0.15 meters, and we know the formula V equal F lambda. Therefore, it gets you lambda equals 0.15 times V, because this is a quarter of the whole cycle. And that gets you 0.6 meters. And since it states that the air speed, the sound in air is 342 meters per second, we can get that 342 equal to 0.6 F. And F ultimately gets you 570 hertz. Now, to answer this question, firstly, the wavelength is 0.6 meters, and the fundamental frequency of it is 570 hertz. Now, a little interesting fun fact. Through some research, I found out that the organ pipe and as well as my beer bottles both resonate best at its fundamental frequency, which is why I found out fundamental frequency instead of any other frequencies, because it is a lot more significant. Now, calculation number 2. Like I said earlier, there are different surrounding environment that would change different factors of this experiment. Now, temperature is one of them. Now the question states, in my house, the temperature is 22 degrees Celsius. Find the speed of sound produced by the instrument. Now, through some research, I found this formula that V, standing for the speed of the sound, equals to 331 plus 0.59 temperature Tc, which means temperature in kelvins. That means for every increase in 1 Celsius, the speed of sound increases at a rate of 0.59 meters per second. Now, what are involved in these questions? Firstly, it is the Tc, standing for the temperature in Celsius. Like you can see here, it is 22. V, the speed of sound. And we know that Tc equal to 21 Celsius. And we know the formula that V equal to 331 plus 0.59 Tc. Then we can simply find V2 by plugging in the numbers. So V that will ultimately get you 331 plus 0.59 times 21, which will get you an ultimate answer of 343.39 meters per second, which means that at 22 degrees Celsius, or in my house, the sound travels at 343.39 meters per second. And this shows that due to the temperature, speed of the sound of the instrument is changed as well, which proves my previous point. Now here is a page of the works cited, and if you have any questions, please feel free to contact me, whether it's through Teams or any other method. Thank you very much for your time. And just before we go, here's a quick demonstration of what the different volume does to the instrument. This bottle has the least amount of liquid in it. This bottle has more liquid than that previous bottle. And last but not least, the white liquid, which has the most amount of volume in it. These are all water, and I just simply color them with food coloring. Now let's try to blow them and see what they sound like. Sometimes it doesn't work. I still need some practice. As you can see, it makes a pretty low-pitched voice. But however, sometimes that one doesn't even work at all because of how little water there is. Now, here's a bottle with the second most amount of water in it. It's a higher pitched voice sound, which is as expected. Now, the bottle with the most amount of liquid in it should expectedly have the highest pitch and highest frequency. It didn't really work out to the way that it would, but let me give it one more try. Technically speaking, this one should had the highest pitch, and I've done this experiment a few times before. It worked. However, sometimes I just still need more practice, and these aren't the most reliable instrument. However, I've done a few experiments before, and it did turn out the way as expected. Thank you very much for your time. If you have any questions, please let me know.